Okay, there's a number of videos out there regarding the lab rabbit. I'll put them over at the chat. I'll use the same for our whole department down except for 305 and 300. Well, I shot 300. They did the same write-up. Now the deal is, the pre-lab part of the lab write-up is your key to do the lab. Now, my policy is on your first lab, you can fix everything that's wrong. So if you forgot to do the pre-lab this week, it's okay. But starting next week, it won't be okay, and you'll have to miss the lab. Okay? Pre-labs are really important for two reasons: safety and organization. Okay, the labs count 10 points apiece, which are the same kind of points that tests are rated on. So I class lab points with easy points. So you want to maximize your easy points to go against your hard points. Now, lab write-ups are easy, but they're just long and tedious. Because everything must be done by hand. Okay, I've talked about this already, but you'll need to get a lab notebook. Leave the first couple of pages for the table of contents. And this is an okay one. Anyway, if you'd like to come up afterwards and look at this, you're more than welcome. I'm going to show you, though, what exactly through scans what this looks like. Okay, begin each lab on a new page. You should have plenty of room in your lab notebooks to do this. So start every new lab on the right-hand page. Secondly, one-sided only. Don't write on both sides. Spiral notebooks won't be accepted, but you can use your electronic devices. Some of you already asked me about that, and that's fine. You have to write on it, not type on it. Okay? And what's nice about doing that is it automatically, very easily creates a PDF file to upload. If I was in your shoes, I'd be doing it electronically, so just FYI. Okay. Your pages need to be numbered because your table of content is going to reflect the lab page number. Indelible ink, except for electronics, obviously. Indelible ink in blue and black. Now, I don't mind you doodling on the pages to make it personal at all. You can also use, for the titles and stuff, you can use different colored pens. Okay, no pencils. Pencils are great for worksheets or dry labs, but not for wet labs. All your mistakes need to be readable. In other words, if you make a mistake, you put a line through it, so I can read your mistake. Put the correction above or to the right. Okay. For each chemical you use, you're going to have to write a first aid procedure book. The easiest way to get that is with something called SDS document. That stands for Safety Data Sheet. Every manufacturer, every legitimate manufacturer of chemicals, by law, has to produce one of these. And they're available online. Okay, so you need table of contents. And you'll need a materials list along with the receipt. Okay, in every lab, no exceptions, needs to have a conclusion, regardless of whether it says right one or all out. Conclusions are worth 3 out of 10 points. And I'm not expecting pages, I'm expecting a paragraph. So, and basically you sum up what you've learned. Okay, I'm not doing any graphs, so we don't have to worry about this. Okay, so notice there are 2 signatures. The one on the right is whether you did the pre-lab or not. The one on the left is whether you cleaned up or not. So before you leave lab, make sure I look over your area and I sign it. Otherwise, you're going to lose very easy points. Obviously, you have to title the lab, its purpose. Like, why are we doing the lab? Usually there's a background section on your lab packet on the particular lab. You usually get it from there. Like on this week's lab, the purpose could be understand better alcohol reactions, primary, secondary, tertiary, something like that. Notice handwritten. Okay, so the first aid. Okay, so what we're going to do is I'm going to jump over to Windows. And to find the first aid information, you're going to just do a Google search on SDS space the chemical name. Let's say hydrochloric acid. Now it's going to give you a whole bunch of, it's over 2 million search results. Okay. Fisher is good. Fisher is good. Let's see. Let's just use the Fisher one. Now it's going to be a PDF file. It's going to be a PDF file. Come on. Well, maybe we won't use that one then. Okay. Now, all the SDS documents follow this format internationally. It depends on what class you take next. I don't, is anyone taking any more chemistry after this class? Okay. I'm gonna say for your next class, sometimes you may keep your this as well. Like, 405, 402, those classes, probably number one. We're gonna be interested in section 4. Section 4 is first aid. And what you're going to put in your notebook is this here. So I want you to be cognizant of any chemical you can potentially come in contact, so that you'll know what to do if for some reason or you get it on your skin, you inhale it, or you ingest it, or get it in your eyes or something like that. Now, I don't believe in busy work at all. So this is on hydrochloric acid. Okay, so 3 labs from now, your acid is hydrochloric acid again. That's in the first aid. You just have to say C lab 3. Okay, you don't have to recopy it and all that stuff. All right, if by chance you are breastfeeding, pregnant, or trying to become pregnant, I suggest you go down to section 11 on toxicology, and it'll tell you whether this is a teratogen or carcinogen. Now, if that's B, just tell me what you're going to do is you're going to let your lab partner do all the touchy-feely stuff for the chemical. And I want to protect your little guy. Also goes for guys if you're trying to become pregnant with your partner. Okay, so that's the STS. Any questions about finding the STS number 1 or what to look for once you're in it? Okay. We are going to can that. Okay. Here's another example. 2 signatures, title, purpose, procedure. What's not on this is a materials list. Notice if you write on one side of the page, you won't get this blue. That's just based on the quality of the paper and what kind of writing you write through. Some go through really well, others are fine. Like the old-fashioned ballpoint pen with a little ball in it works fine. That's why we're only writing on one side of the page only. Okay, data table. Most labs are going to require you to do a data table. Purpose of the data table is a place to store your information. Sometimes it's a combination of recordings plus calculations. Now, when you're putting down numbers, I don't know if they went over this in 305 or not, but whenever you're dealing with numbers that are less than 1, you need a 0 out front, so 0 point. Also, your data needs to have units. In this case, it's temperature in degrees centigrade. We're not going to use Fahrenheit or Kelvin here, but always going to be C. The typical data table you've got is rectangular. Across the top are the titles of what the data is. And going down the left side is for each element of the lab. Okay, so that's the pre-lab part. So title, purpose, procedure, materials list, which I don't think this is in here either. Oh yeah, here it is here. And then that is your ticket to get in the lab to do the lab. After next week, again, if you don't have this pre-lab done, you cannot do the labs. Okay? By using easy points, 30% of the lab is based on your pre-lab. 30% is also based on your conclusion. Okay, so this is basically it here. Let's see. I'm going to jump over. Well, you're typically going to do not so much calculations in here in our class, but you're definitely going to have questions. And you frequently will have unknowns. For example, the lab this week, you're going to have an unknown. You're going to be working in groups of 2 or 1. 2 or 1, not 5 or 6. Sometimes next week's lab, you're going to be working in groups of 4 or 5. Also, next week, you need to bring in an orange. We need about 4 oranges per group. That's when we extract out the oil, the essential oil from orange peel. Okay, so that's basically it on the lab write-up. Are there any questions about the lab write-up? And remember, your first lab, I allow you to fix all your mistakes. So theoretically, everyone here should get a 10 out of 10 on the first lab, unless you don't want a 10 out of 10. But everyone should get a 10 out of 10. Okay. Okay, where is... Now, I went over aldehydes and ketones last time we met. And I'll look at last week. And I want to go over some of the reactions in the food. Because in this, starting now, you're going to have a primary and secondary backbone, and you need to be able to identify it. Okay, so let's. Okay, so there are reactions with alcohol, and they are oxidized or reduced. We talked about this in Unit 1 as well. So if you oxidize a alcohol, let's say you oxidize that is 1, 2, 3, 4. So that is a 2 butanol. And secondary alcohol oxidized to the ketone. So to name this is going to be 2-butanone. So ketones are going to have the functional name ONE. If you want to create an alcohol, you can do the opposite of oxidation, which is reduction. So say we wanted to create that. Okay, so that's going to be 1-butanol. Okay, there's a couple ways to make that. One way is if you start with an alkene, put water across the double bond. The other way is to reduce an aldehyde. So let's do on both. Okay, so let's do the reduction first. So oxidation, we remove hydrogens. Reduction means we add hydrogens. So in this case, we are adding a hydrogen there. So to name that, it's going to be butanal. It's an AL. Now, AL and OL kind of look the same if you write sloppily like I did. Make sure you get that functional group name properly. Okay, the other way to create an alcohol is through a double bond, an addition reaction across the double bond. Now you can put H plus or H2SO4. Either one's fine. Okay, so we're going to start with butene. We're going to end with butanol. Now we're going to get a mix with that. We're going to get the 1-butanol and also 2-butanol. Okay, and the 2-butanol is the more stable of the two. Two reasons: symmetry and the carbon top. Number of terminal hydrogens is more at the bottom of the top. Excuse me, the top one than the bottom. Now, you remember in test one, I did ask you to create an alcohol. And so the answer to that problem is that right there. Let's start with the alcohol. Okay, so that's oxidation reduction of aldehydes and ketones. Then the addition reaction across the double bond with water. Those are the two main pathways to get to either an aldehyde or a ketone. Okay, the other kind of reaction, another class of reactions, is creating acetals and ketones. I went over this last time, but I want to go over this again. This is key to carbohydrate metabolism. Key. Everything that goes on with an aldehyde and a ketone chemically also goes on in your body with things like glucose, allulose, fructose. Same reaction. Okay, so an acetal has got an OCO. As soon as you see OCO, you automatically have an acetal or ketal, or the hemi versions of either one of those. So you have four possible structures if you have OCO. The first reaction with, let's talk about an aldehyde. The first reaction we come to is the hemi-acetal version. If we keep adding alcohols, that'll further go on to full-blown acetal. If we started with a ketone, same reaction, only we're going to end up with a ketal or a hemiketal. Now, this reaction is not as common biochemically. In fact, what your body does, it converts the ketone to an aldehyde, then it reacts. That's all done enzymatically. Okay, so let's go over again this whole bit. Now, let's first of all, I'm going to put a dot where the anomeric carbon is. In carbohydrates, that's the carbon that does the reaction. It all centers around the anaerobic carbon. Usually it's carbon number 1 or carbon number 2. Most of the time it's carbon number 1. Fructose is going to be carbon number 2. Oh, when we start carbs, I'll show you that. Okay, so let's look at this. All right. All right, so let's name this guy. Excuse me. Well, so the main backbone has to go through the anomeric carbon. And the anomeric carbon's got an oxygen either side of it. So we have O, C, O, yes. We have H present on the anomeric carbon. No. So we have OH coming off of the anomeric carbon and no again. So this combination yields a ketal. Remember now, carbon has 4 bonds. If 3 are coming out of the carbon, that 4th bond is going to be hydrogen. And that will be the secondary backbone. So if we hydrolyze this, the alcohols are going to come off, leaving you with the original ketone or aldehyde. So let's throw in some acid and we end up with, so this would be the first time it hydrolyzes, we get the hemi. And since we've identified this as a ketal, we're going to end up with a hemiketal. So we're going to have one of the alcohols come off. And then the remaining one. And that leaves behind an OH. Now, if we let it go on, we end up with the other alcohol. And that's what made up the backbone, or the secondary backbone. So it's important to see where all those alcohols originated from. When we start hydrolyzing. Now, if we hydrolyze a acetal, we get something similar. Let's do the same reaction. Okay, so this is OCO. That means we have something. And we have a hydrogen here. And we have no OHs. So this is going to start with an acetal and generate. Now let's put in our backbones. It's going to first kick off one alcohol. So it's going to create a hemiacetal in this case with continuous. Oops, so we can put them together, we can take them apart. We put it together, aldehyde or ketone, add alcohol. And it's in 2 steps. If we start with an acetal or ketal, it'll disengage or hydrolyze into the two alcohols plus the original aldehyde or ketones. Now, okay, so this is glucose now. Lots of OH groups, a lot of alcohol reactions, glucose participates in. But one thing that is very different about carbohydrates, they have an anomeric carbon number 1. That means it can come apart to either a ketone or an aldehyde. And secondly, it's usually found in cyclic form, which is more stable than the open form. So let's see what kind of stuff we got going here. Okay, so we've got OCO. That means we have something. Carbon number 1 is the anomeric carbon with hexoses. So what's going to happen is, first of all, let's identify. It says OCO, yes. Okay, and do we have H present? Yes. We have an OH present? Yes. Hence we have a hemiacetal. Now it's crucial in this unit. One, you be able to identify the OCO. And secondly, what happens when the ring structure opens up? What happens when it opens up, it goes from a hemiacetal to an aldehyde. So this is a hemiacetal. Now it's going to open up to the aldehyde. Now it can undergo any aldehyde reactions. Now aldehydes are fairly unstable. They're very susceptible to oxidation. That's one of the main routes how we identify aldehydes is through oxidation. So if we oxidize that opened up glucose, let's say a copper 2 ion, what's going to happen is in an alkaline environment, what's going to happen is that copper is going to oxidize that aldehyde to an acid. And because it's in a alkaline environment, we get the salt of the acid, not the true acid. Now, so this guy here, aldehyde to acid, is oxidation. So if something's being oxidized, something else needs to be reduced. It's going to be this guy here. It goes from a +2 to a +1. So when reduction happens, the charge is reduced. And how many electrons are involved. Okay, and this reaction is very important. You can see it time and time again in this unit. And this particular one is called Benedict's test. Now what happens is that copper +1 ends up commingling with some hydroxyl ions, and you end up with this rusty color. And this happens like that, very fast. So in today's lab, or this week's lab, whenever you do a Benedict's test, that reaction will go within seconds. Your lab procedure says wait 2 minutes. If there's a color change, you're done. You don't have to wait 2 minutes. And you're going to find Benedict's reaction and go boom. So that's one way to tell whether we have a is with a hemiacetal present, using the Benedict solution. I'm really doing this in lab today and some other tests as well. Because this just pure alcohols, you need to distinguish primary, secondary, tertiary. Now, Benedict solutions if we have an aldehyde, aldehydes can be oxidized. What if we have a ketone? Okay, so that's a, oops. Nothing, oh. Okay, so, the ring is closed. What happens if the ring opens? And all cyclic sugars will open and close. Most sugars you're gonna find when you put out either carbons long, 6 carbons long, or 4 carbons long. Mostly 6 carbons, the most stable of the bunch. So, what's going on here? Well, can we oxidize this? If this in Benedict solution. What's gonna happen? Go from green to rusty color. One way or the other. What do you think? Yeah. Oh, you're touching your hair. Okay, what does not oxidize? Ketone. Exactly. So this will have no reaction. Let's do a couple more reactions with um, aldehydes and ketones. No, but this is really important, you guys. Real important. So on this next test, you're going to have 1 3x5 card. So think about the reactions or structures on that 3x5 card, both sides. On one other thing, um, if we go to files, unit 2, worksheets, you'll find some more worksheets to practice this. Now, I've included the answers as well. So you can see these are OCO, OCO, lots of acetyl and ketyl reactions. Okay, so let's get into carbs more now. Okay, so with carbohydrates, we're going to add to aldehyde ketone chemistry. Now, carbs and fats or lipids have been around a long, long time. So people tend to use common names rather than IUPAC names. Now, as you know, carbs provide energy. When we go through the metabolism of glucose, we're going to see the last series of operations is a phosphorylation series of reactions, creating energy molecules called ATP or adenosine triphosphate. So glucose burns really well. If the body needs energy, and glucose is not around, it'll convert glycogen first, then your fat, and lastly your muscle into glucose. Because your brain requires glucose. It doesn't work on fat, doesn't work on protein. So process of creating glucose is called gluconeogenesis. Okay. Okay, carbs are polyhydroxyl, either aldehydes or ketones. Actually, I'm going to modify that. Aldehydes, ketones. Something called polyols. Now, polyols are basically ring structures, only they don't have an aldehyde ketone backbone to it. And they use them a lot for artificial sweetening. Okay, so not very frequently you'll see mono carbs like fructose, glucose, ribose, opened up. And this is what they look like opened up. So, and by standardization, the aldehyde or ketone is at the top, and all the hydroxyl carbon combinations are below that. Okay. So this is going to be where the aldehyde or ketone is going to be the anomeric carbon. Now, all the reactions center around the anomeric carbon. There are four giant groups in the study of carbohydrates. Monosaccharides, disaccharides, meaning two monosaccharides come together, oligosaccharides containing monosaccharide with three enzymes. That would be glucose, and then, as an example, some of the baby formula have some whole raffinose set into saccharide. And anything bigger than this is called polysaccharide, like starch, cellulose, etc. Now we're going to be studying all four of these groups. Now, I just picked up some meds a couple days ago, and I talked to the pharmacist, and I have an inhaler. It's an albuterol inhaler. I cleverly left it home. Anyway, the new albuterol inhalers utilize L-albuterol. And she was trying to explain to me, I said, what's the difference between this and regular albuterol? And she said, well, the LEVO, L-E-V-O version works better than the other one. I said, are you talking about an enhancement? But, oh, yes. I said, you okay with that? Anyway, so this concept of mirror images of one another is an incredibly important aspect in biochemistry and organic chemistry. Who's heard of the thalidomide? Here that went on in the 60s. Anyone? Thalidomide was given to pregnant women in the first trimester for nausea. The given was a mixture of the L and D version of thalidomide. So one of them worked really well, decreased nausea, and the other one caused horrible birth defects. The babies died in the womb. It came to labor, and they actually came out, and they lived. They would have no arms, no legs. The woman, and it was because of your images from them. Our bodies are extremely sensitive, whether we're looking at, and letter hereditary refers to the L here. Which version? Now, look at your hands. Okay, one palm, 4 fingers, 1 thumb, and they're all connected together to the palm, right? But why critically are these two chemicals not the same? It's because you cannot superimpose your left hand and your right hand. Just line up the fingers, but the thumbs don't work. Now, anytime you have a chiral carbon, you can get D and L isomers. So, when the card is opened up like this, and you look at each carbon on that molecule to determine if it is a chiral carbon or not. Now, chiral carbons require 4 different groups attached to that carbon. If the chiral carbon exists, we can D and L. If there's no chiral carbon, then we'll do the D and L version. Now, you've heard of cis and trans fats. In carbohydrates, we're looking at D forms of the carbs in our body, not the L forms, the D forms only. Now, everything is the same between the D and L form, except for there's a chiral carbon there. Frequently, there's more than one. Like, for example, here, we've got, is this chiral carbon? No. You're going to have 4 groups coming off the carbon. This only has 3. You've got We've got the double bonded oxygen, carbon hydrogen bond, and a carbon carbon. So that is not four independent groups. Look at the second one. We've got an H2, an H2, an H. We've got a this group down here in the bottom, CH2OH. And we have the OH, and we have this aldehyde group at the top. So four different groups. Hence, D and L is going to exist with this molecule. Now, it's very hard to separate these from the L. Oh, but the industry has got a lot of application techniques to differentiate that. Okay, so chirocarbon. You'll see that on a lot of standardized tests. If you're applying to med school, you will see that as a question. Does this molecule contain a chirocarbon? All right, so let's look at this here. Well, we've got 1, 2, 3, 4, 5, 6 carbons, so it's going to be a hexose. And because it's got an aldehyde, it's going to be a hexaaldose. Hexa means 6. Aldose means it opens up to an aldehyde. So let's go through these carbons one by one and look at how many chirocarbons we've got. Okay, so carbon number 1. Well, we've got 3 groups, not 4, so that's definitely not chiral. Carbon number 2, we've got 1, 2, 3, 4 independent unique groups, so that's chiral. The next carbon down is we have 1, 2, 3, again, 4 independent groups. Carbon number 4, we have 1, 2, 3, 4 independent groups. And carbon number 5 is we've got 1, 2, 3, 4. So carbon 5 is chiral. And then that leaves this guy down here. What about the carbon here? It only has 4, actually we have 3 independent groups. It's got 4 bonds, but 2 of them are the same. CH. So it's got 2 CHs, 1 OC, and then 1 carbon-carbon. Okay, so this hexose has got 1, 2, 3, 4 versions of it. You know, in all the different combinations, that one molecule. Okay, if you look at the three-dimensional model of this molecule on the left and the right, what we do is we project them into the paper. So we go from 3 dimensions to 2 dimensions. This is called a Fisher projection. So again, the aldehyde or ketone needs to be at the top. So what they've done, they standardize, because chiral carbons exist, means there's D and L versions. So how do you know if you got a D or an L? Well, in this projection, you look at the last one or the farthest one from the aldehyde or ketone. That's this guy here. If it goes to the right, it's a D. If it goes to the left, it's an L form. Now, we're mostly going to be working with another kind of projection. Oh, in a minute, I'll show you. Also, if there's a chiral carbon present, it will rotate light. It rotates it to the left or the right. Now, my first undergraduate research was with a carb chemist, and he was trying to synthesize in a test tube sucrose. Very hard to do. And we use this instrument all the time because the more it's rotating, the higher the concentration. You actually calibrate it. Okay. And these are called enantiomers of one another. Okay. We get to unit 4. In unit 3, we're going to be working with acids. Lots of amino acids specifically. Okay, they're chiral carbons, every one of them except for one. And those are in the L form. Carbs are in the D forms. As far as natural ones. Okay, step number 1, when you're trying to organize what kind of sugar it is by the number of carbons. So hexose is going to have 6, pentose 5, etc. Now these are in heterocyclic forms. Like this would be a hexose. That would be a pentose. And then we need to distinguish whether it's a keto base or an aldehyde base. Okay, so basically, if we started with 6 carbons, we're going to end up with 16 variations of that 6 carbon sugar. A or D, A or L. We're not doing anything with the L, only D. So really there's 8 versions. And as we build the number of carbons, the carbon in the middle is going to be the carbon. Also the amino carbon. So also the chiral parts. Okay, so as we increase the number of chiral carbons, we increase the complexity of the combination. And you're going to be required to know glucose or lactose. And you need to know it all the time. You have to know the rest of it, just know there are 8 of them. In fact, there's a brand new sugar substitute on the market. It's called allulose. And allulose is a 5-ring sugar that looks almost like fructose. Almost. That's the key. So it's as sweet as fructose, but it doesn't get metabolized. So the enzymes that metabolize glucose or fructose can't recognize allulose. But this is fairly new, like within the last year or two. It's kind of hard to come by. That's why you haven't seen very much of it. And curiously, has anyone used allulose? I haven't either. I need to buy some next time I go to the store. Okay. Unfortunately, carbs are sweet. Except for that. Starch. Small ones, though, are very sweet. Look at fructose. It's almost twice as sweet as sucrose. So the structures we're normally going to be using are the Hayworth structures. Okay, so we always draw on the right side of the structure the anomeric carbon. Doesn't matter whether it's a hexose, pentose, doesn't matter. Always drawn on the right. And the anomeric carbon can have its OH group up or down. Now, this happens to be galactose. Galactose is also a very common monosaccharide. And when it's the OH is going up on the anomeric carbon, it's considered a beta version. When it's going down, it's the alpha version. And those can interchange because as it opens up and it reforms again, that OH group, carbon number 1, can be up or down. In a lot of your textbooks, particularly biology textbooks, do not show the difference. In fact, they frequently don't even show how. Hayworth, they do another version. Okay. So, this is glucose. Now, the way I normally draw it is like this with none of the H's. But if we were drawing all the H's in, it'll look like this. So, this is the beta version because the OH goes up. When we interconvert it, in other words, when the thing opens up, it becomes the aldose version, exposing an aldehyde, and then it'll come back down to the alpha version. It opens, closes, open, closes. When it's open, it's very vulnerable. And when it's closed, it's more stable. That's why you find most of the monosaccharides as cyclic. Now, whenever you see a monosaccharide, you need to analyze for the presence of a heavy acetyl. Because those are the ones that are going to react really fast. The others won't. Okay, so here is glucose, and it's in the beta form because the OH is going up. So we have, again, OCO. And we have a hydrogen, yes. And we have an OH, yes. Hence, hemiacetal, which makes that open up. Now, the general classification of a five-membered heterocyclic. Hetero meaning it's not all carbons. It's got an oxygen in there. Those are called purinosis. Purinosis are six-membered heterocyclic rings. And again, the reason why the rings form is for stability reasons. Okay. This is fructose. Now, again, the OH on carbon number 2. Okay, so five-membered rings. The anomeric carbon is carbon number 2. Big difference between fructose and glucose. Six-membered ring, five-membered ring. The first stage of carbohydrate metabolism is phosphorylating carbon number 6. Second step is phosphorylating carbon number 1. So that's unit 5. Okay, okay, so all monosaccharides, no exception, are all reducing sugar. Okay, so what a reducing sugar does okay, so a reducing sugar reduces the non-sugar in the solution. In the case of Benedict, the carbon, copper +2 plus the copper 1. That's the reduction. So in this case, okay, so let's look at a situation you're going to run into this week in lab. We're going to be doing a lot of this stuff exactly right here. Okay, so we've got like let's go to the okay, so here we have Benedict's solution. A nice blue copper +2. And we have two glucose solutions of varying concentrations. So when we dump that in here, if it changes color, which went from blue, that ugly rusty brown, that means the copper +2 is reduced to copper +1. You don't know which sugar it is, though. Other than it's a reducing sugar, reducing sugars, hemiacetal has to be present. So you know it's hemiacetal. Could be galactose, glucose, fructose, a number of them. And again, you're going to put it in hot water. And within seconds, it's going to do this. Okay, we can also take the OH and react it with an acid to form an ester. This is unit 4 stuff, so don't worry about that. And one on the left here is the first step of glycolysis. You take glucose, phosphorylate, from the second step is the phosphorylate. That got it from the Now, I want to do one more thing. Okay. Now, whenever we form this time, previously the alcohols were sick. I'm going to have to quit. I'm really short of breath right now. So we're going to pick up on Thursday right here.